So the input protection, of course, becomes most important at the first op-amp that is connected with the outside world. All the other op-amps in series here are only connected to the outputs of other op-amp. But the first op-amp, of course, has to be maximum protected. And first of all, we want to keep DC voltage away from the op-amp input. So we just put a capacitor with a rating of at least 100 volts, because when we know our peak voltage here could be 60 volts, of course the rating of the capacitor must be 100 volts. Now there immediately comes a trap for young players. If we have an input of an op-amp, no matter if it's the inverting or non-inverting input, if we have it only coupled with a capacitor, then the current, the bias current flowing either outside of the op-amp or into the op-amp, and which is always present, no matter if you choose bipolar op-amps, FET or CMOS op-amps, this would charge up the capacitor, and it's only a matter of time when the voltage here through the charging by the bias current reaches the supply voltage, and then your op-amp input is kind of blocked. And this happens to every designer of every age, that you at some time forget to add a resistor. This resistor could go either to one of the supply voltages, or depending on if the bias current is flowing out or into the op-amp, it could also go in theory to the output. So you always need a connection. Here the easiest way is just to put the resistor to ground, so that our bias current flowing in this case out of our op-amp doesn't charge up our input capacitor. Now, is this protection already sufficient? Well, no, it's not, because if you know that at the instant when you connect an outside voltage to a capacitor, the capacitor has zero impedance. So if you put a power amplifier with basically zero output impedance directly now to the capacitor, there would be an incredibly high current be flowing here and certainly destroy your op-amp. So we still have to limit our current simply with a series resistor. And now we can safely, if the dimensioning of the resistor and the capacitor is adequate, we can now simply connect even a fully turned on power amplifier at full output level with our circuit. At any instant, the input of our op-amp won't be damaged. But now comes the first moment where we have to look into our datasheet just to see what is the maximum short time input current that is allowed here at the input in case of overvoltage. So now we finally, of course, need the datasheets, because in this case we already know a chosen op-amp, the NE5534, and this is an op-amp manufactured by many second sources. You best go to a datasheet search site like Datasheet.com or any other. And if you input NE5534, you see there are at least 3 different manufacturers: NXP or Philips, TI, and ON Semiconductor, formerly Motorola, as far as I know. And you should download all of them, print them out, because it's often the case that one datasheet gives you one important extra information which is not present in the other ones. And you also should search for application notes, because there are also quite often useful informations. And I've already done this. Well, let's search for an application note. And for example, here it looks like, well, where do we have one? I think here, this looks like a real application note. AN for application note 142, audio circuits using the NE 5534, 33 and 34. And let's see what we get. Yeah, this is an original application note from NXP Philips, dating from 1984. So this part is, I think it's around 40 years old. And also print this out, and we will later see that really in this application note there is one very important information that we later need. We won't go into all of the details of the NE 553 series, but what we want to know is what is the maximum input voltage, or better, the maximum input current. And you usually find this in the absolute maximum ratings, but here it's not, so it must be hidden somewhere else. Here. And that's why you should really carefully read your datasheet. Note 1. Diodes protect the inputs against over voltage. Therefore, unless current limiting resistors are used, large currents will flow if the differential input voltage exceeds 0.6 volt. Maximum current should be limited to plus minus 10 milliamps. That's what we need. The maximum input should always be limited to 10 milliamps. And this is a typical value for the maximum current into the inputs. So we can use this 10 milliamps not only for this op-amp, but for many other op-amp, but always carefully consider your datasheet. So we finally have the necessary data to calculate the value of our input resistor R1. We know that the maximum current through this resistor must always be smaller than 10 milliamps, and the maximum voltage where this can occur is, to be on the safe side, 100 volt. And now Ohm's law simply gives us that the minimum value of R1 is the maximum voltage divided by our maximum current, and that gives 100 volt divided by 10 milliamps gives us 10K. So easy as that. 10 kilo ohms or larger. We will later discuss if it makes sense to make this larger for a kind of extra protection, or if it's better to leave it at the minimum value. Now what remains is, which value shall we give to our bias current deflection resistor, as we could call it, R2. Now we immediately see that R1 and R2, if we for the moment leave out C1, they make a voltage divider here concerning the input voltage and the voltage at this node, which goes to our positive op-amp input. Now of course we don't want to divide our voltage down for a factor of 10 or 100. So if we would make this 1 kilo ohm, we already would have only 1/11 of the original input voltage. Why not make it the other way around? Let's say 1 meg ohm. Well, there are two reasons which we'll discuss later in detail. First of all, the noise starts to increase when we increase the value of R2. And second is the so-called bias current flowing out of the inputs of our op-amp, which we'll also discuss later. They generate a voltage over R2, and if we make it 1 meg ohm, then this could already be over the top. So we choose the simplest, or we take the simplest choice. We make it the same value as R1, and that would be 10K. So what remains is to choose a value for C1. Now, if you look closely, C1 and R2 are giving a high-pass filter. And we could first of all think, well, we only need a flat response from 1 kHz upwards, so we could set the corner frequency of this low-pass filter just to, let's say, 500 Hz. Well, that's not quite enough. The impedance of C1 is in series with R1, and depending on the frequency, it changes the value of our voltage divider. Just let's take an example. If at a certain frequency, let's say 1 kHz, our lower limit, C1 would have an impedance of 1K, 1 kilo ohm, then we would have a voltage divider of 10 plus 1 to 10, so 11 kilo ohms to 10 kilo ohms. But at higher frequency, the impedance drops linearly. And that would mean that, for example, at 10 kilohertz, we only would have 100 ohm impedance, and so we get a different division ratio here between the combination of R1 and C1 and R2. So we have a kind of combined voltage divider, the sum of R1 and C1 and R2. And we have to make the division ratio as flat as possible in our frequency range that is of interest from 1 kHz up to 20 kHz. Now let's say we are on the safe side. We have set in our specs that, let's get it out again, that our frequency response has to be flat from 1 kHz up to 20 kHz to 0.1 dB or 1%. And now we can calculate the necessary value of C1. Let's first of all note down the formula for the impedance of a capacitor. It's simply 1 on or over, don't know, 2 pi times the frequency times the capacity. That means if we look upon C1 or any capacitor as a frequency-dependent resistor, we know that the impedance goes down with frequency because frequency is in the denominator. So we have to take into consideration our lowest frequency of interest where we need our flatness, and that is 1 kilohertz. So we're setting in for F 1 kilohertz. And if we want to have a flatness of 1% or better, that means that the highest value C1 may have is 1% of R1. That means 100 ohms. So if the impedance of C1 is never higher than 100 ohms, then we have certainly, then the division ratio of our resistor divider here doesn't change more than 1%. So we already know that our impedance at 1 kilohertz has to be 100 ohms. Or to be 100% precise, it would have to be 1/100th of R1. So if we solve this formula to give us C, then we get C equals 1 on the impedance XC times 2 pi times the frequency. And if we put in the values, we have XC already as 100 ohms times 2 times pi times 1 kilohertz. Take the inverse of that, and this gives us 1 point, let's round it up to the next E12 value, 1.5 microfarad or larger. So we have our value for C1 as 1.5 microfarad or larger. And now let's sum it up. What are three elements which are now determined, what they finally, except for the input protection, what other effects they have. First of all, because at all our frequency range of interest, the impedance of C1 can be neglected. We have a simple 1-to-1 voltage divider, which means at the positive input of the op-amp we only have half of the input voltage. That means we have a minus 6 dB attenuation. That's the first effect. And we have a high-pass filter, so any low frequency below 1 kilohertz is filtered out. If you want to know the corner frequency, you might think that this helps in filtering out 50 hertz noise. Well, let's see. The corner frequency of a low or a high pass filter is 1 on 2 pi times the resistance times the capacitance. So we know C1 is 1.5 microfarad. R2, which is the second element of our high pass filter, is 10 kilo ohms. Let's do the math. Clear all 2 times pi times 10k times 1.5 microfarad. Take the inverse again, and we get 10.6 hertz. So let's round that up to 11 hertz. So we have a high pass filter with a corner frequency of 11 hertz. So we don't get, and that is the so-called minus 3 dB frequency, so we get a perceptible attenuation only of frequencies below 11 hertz. So sorry, we don't get any 50 hertz mains noise hum suppression here with that, but we can't get away with that because the value is determined by our 0.1 dB flatness requirement. And we know by the choice of the elements that now our flatness is guaranteed from the flatness concerning 0.1 dB from 1 kilohertz up to, we could say infinity, but we will say later there is a practical limit due to other factors in the next op-amps that we neither need more than 20 kilohertz, nor will we get it by practical limitations of the circuit design. Now, simple as it was, our our input protection circuit has developed into an attenuator and a high-pass filter as additional effects of these three elements. Now let's just check if our real attenuator does give this flatness, and I've left the values of the input resistor and capacitor at their original value. The original designers choose a 10 times different values. For R1 and R2 they choose 100K, and correspondingly C1 can be then 10 times smaller, so it ideally would have to be 150 nanofarad. They choose 100 nanofarad, so the flatness should at 1 kilohertz be a little bit worse than 0.1 dB. And I think the reason the original designers choose here 10 times larger resistors was simply a practical limit for the capacitor, because at that time plastic film capacitors of 1 microfarad or larger were not only bigger in size but also more expensive. So that's perhaps was the reason. But we also will see later that our choice here is near optimum concerning other things like noise, etc. So let's check the frequency response of, first of all, our input stage. We could use the onboard sound card of a PC together with a audio analyzer software, but now here we'll make it so that you can see everything on one display with my multimeter, because I can set it to displaying dB mode. I've set the frequency now at, where are we? 1 kilohertz, not 100% exact, one digit out. And the nice feature is we can null out our, or we can set our 0 dB reference value simply with the relative function. And so we have set now our input voltage to 0 dB. And now let's go to the output of our op-amp and see if we measure the 6 dB attenuation. Just a second. Yes, we're at minus, we're at minus 6.04 dB. So that's exactly what we expected. Now let's take this now as 0 dB because we want to check the flatness. Null it out again. And now we slowly increase the frequency to, and let's see if we see anything changing. We're now at 2.7 kilohertz, 4. So everything remains within 0.1 dB. We're now at 8 kilohertz, 10, 12, 15, and finally 20 kilohertz. So everything within 0.1 dB. So that is quite okay. Now for a comparison, we'll go directly to the output of the last stage before the AC to DC converter comes, and let's see if our whole chain of 3 op-amps is frequency linear between 1 kilohertz and 20 kilohertz. So here we are at pin 6. Let's null this out again. We're now at 1 kilohertz, and I'm again increasing now in 1 kilohertz steps. I'll make it a little bit slower. 1 kilohertz, 2, 3, 4, 5. We see a slight decrease in level. Now we're at minus 0.11 dB. 10 kilohertz, still okay. 15 kilohertz. And 20 kilohertz. So the frequency response is linear within 0.1 plus minus 0.1 dB from 1 kilohertz up to 20 kilohertz. So that's verified. So our input protection circuitry has finally developed into an input attenuator as well as a filter. But if we remember what input voltages can be present at the input, we had 100 millivolts RMS up to 40 volts RMS. Let's see. The 100 millivolt RMS is here at this node, which goes to the input of the op-amp. This is simply divided by 2 to 50 millivolt RMS. But what happens to our maximum volume value of 40 volts RMS? This translates to 20 volts RMS, or in other words, 28 volts peak, or 56 volts peak. And that is still too much. Now we have to make a compromise. We could of course say, if we make the division ratio between these two resistors from 1 to 2 down to 1 to 6, so that we get only 1/6 of the input voltage here at the op-amp input, then we would be on the safe side. Let's just do a quick calculation. 40 volts RMS divided by 6 gives us 6.67 volts RMS at the input. And of course we have to know the peak value again by multiply by the square root of 2, which gives us plus minus 9.4 volts. So that would be okay. But then we get another problem. This time we not only divide the highest voltage by a factor of 6, but also our lowest voltage. So our 100 millivolts RMS divided by 6, what remains is barely 16 millivolts. Now all noise, etc., has to be 90 dB below that full range voltage. And that means again we have to divide 90 dB is a factor of 30,000. We divide this by 30,000 and we get 500 nanovolts. So our noise and all other unwanted signal sources have to be below half of a microvolt. And there the problems start to creep in, because then our op-amp also has to have noise below 1 microvolt. And that becomes really difficult. The here used NE5534 is already a very good low noise, low distortion audio op-amp. So it's also, although it's quite cheap and very old, it's still one of the best audio op-amps concerning noise, distortion and other factors. But if we go too low, then even here noise starts to become a problem. We could get away with this with an ultra low noise, low distortion op-amp, which is substantially more expensive, like the LT1028, I think, is one of the ultra low noise op-amps. That will be one remedy to get to a better and more expensive op-amp when we change the division ratio here from minus 6 dB or a factor of 2 to a division ratio of a factor of 6. We of course would have to recalculate the value of our capacitor, etc., but that's not the problem. So the second best thing is we say we keep it as it is, and if we connect our input really with the output of a high power op-amp, we'll add another divider looking simply like that. For example, we could say we would have to add a factor of 3, so we say we make this here 1K and this 470 ohms, and so we get here a division ratio, oops, you cannot see it, a division ratio of 3, again another division ratio of 2, and so we're finally on the safe side. So that is the second best thing, and that is exactly what they did at the original circuit. They left it as it is, but mentioned if you measure really high input voltages, then add a simple 2 resistor divider to get away with the high voltages. So is our protection now complete with these 3 elements? No, it's not yet 100% perfect. First of all, you have to take into consideration that you accidentally touch here the input, for example with your body, and your body is charged up with static electricity, and you get perhaps 2000 volts here for a very short moment. So, and you don't find anything concerning ESD protection in the datasheet, at least I didn't find it. The only thing you can find is what we already saw, that the current should be limited to 10 milliamps at maximum. And what we have to concern here with is a positive input, because that is the only one that is connected with the outside world. The negative is connected to the output of the op-amp, and so there we have no external signals that could come into. So how could we do this? Well, one standard way is to use a combination of protection ESD diodes, that if the voltage at this point is higher than the supply voltage, it leads this voltage simply to the positive supply, and a second diode that is connected with a negative supply to give a path for negative input voltages higher than the supply voltage plus the forward voltage of the protection diode. So this is one standard way. Usually these protection diodes are integrated into the amplifier, but probably because this amplifier is around 40 years old, ESD was not of a great concern at that time, and they didn't have this. So this would be one way to protect the inputs, or in this case we only need to protect the positive input with ESD protection diodes. So you cannot take any standard diode. First of all, these diodes have to withstand at least 2000 volts because the standard test voltage for ESD is 2000 volts. And second is, these diodes should be at best ultra low reverse current diodes, because you can see they are operated here in reverse, but there is always a current flowing here backwards or in reverse through the diode, and this flows also here through resistor R2. And now let's make a back of the envelope calculation. If we take a silicon diode with, let's say, 10 nanoamps reverse current, and we have a 10K resistor, this gives an offset voltage of 10 nanoamps times 10 kilo ohms, which translates to 10 nanoamps times 10K to 100 microvolt offset voltage. So because at this point here in our circuit, these 100 microvolts DC offset, they don't play any role because we don't need a DC exact amplifier here or a DC exact circuit configuration. But if you would be dealing with a DC exact amplifier, which has to be exact to the microvolts range, you cannot tolerate this. So even ESD protection diodes are in some cases not good enough, and you have to take other measures. I will give you a link. You can also use FETs here, which have a reverse current in the picoamps range, and you can also use normal small signal audio transistors, which also have reverse currents in the sub-nanoamps region, also going down to the picoamps region. But that goes a little bit too much into detail. But one way to protect here our circuit for too high input voltages by static electricity would be using two simple, in our case it would be sufficient to have two simple diodes with 1 or 2000 volts reverse voltage. So a 1N4007 diode would probably be sufficient to keep ESD voltage away from the input. Here, in this case, from the positive input. So you have to take this into concern because here this is really connected to the outside world, and you never know what happens when you touch this input. So next thing we have to deal with when protecting our inputs is, what about the negative input? If you take a close look at the datasheet, you will see that between the positive and the negative input there are two back-to-back diodes. And now, as long as the op-amp operates in a normal way, there is no voltage difference between the positive and the negative input, and of course none of the two diodes is conducting. But could there be a state when, for example, the negative input is 0.6 volts higher or lower than the positive input? And what would happen then? Well, then one of the two diodes would start to conduct, and there would be a heavy current, and in this configuration as a buffer where the output of the op-amp is directly connected to the negative input of the op-amp, well, if the output is not exactly following the input at the positive side, we could get, in fact, this state. Now again, we have to look into our data sheet and see what is the maximum voltage that we can apply at the positive input, and therefore this graph is the right one. Here we can see the so-called input common mode voltage range. And because we have a supply voltage of 12 volts, that is here, and the positive input can only deal with voltages up to around a little bit higher than 10 volts, and the negative input can deal with inputs a little bit higher than, let's say, 12 volts. So what happens if our positive input is overdriven with a voltage larger than 10 volts? This could be momentarily, but it could also accidentally be repeatedly if we have a too high input sine signal, for example by accidentally connecting it with the output of a power amplifier. Then the output could not follow anymore, and it simply clips at, let's say, 10 volt, and that means if we have 10.6 volt here at the input and the output clips at, for example, 10 volts, then we would have a differential voltage here of larger than 0.6 volts. And then, in that case, the first diode would start to heavily conduct, and in this case in this direction, and allowed is only 10 milliamps, but the output can supply 38 millivolts, and that could destroy our negative input. So how can we deal with this? Well, very simple. And this is often overlooked in voltage follower op-amp circuits. As simple as this circuit is, connect your output with a negative input and you get a simple voltage follower or buffer. But most often this current limiting resistor R3 is forgotten to protect your negative input in case this problem can occur. And well, what value should we make it? Quite simple. To be really sure, this should be larger than 10 volts divided by 10 milliamps, which gives us 1K. So putting a simple 1K resistor in the feedback loop gives additional protection for our, in this case, our negative input terminal. And there is another condition where this could happen, and that has to do with slew rate. If we have a very steeply rising, for example, a square wave at the input, and our op-amp is simply too slow that the output cannot follow fast enough, then of course we also get here a differential voltage simply because of the slew rate, because of the slowness of our op-amp. This could in theory also happen. It wouldn't happen here in this circuit probably, but in other circuit topologies you have to take care of slew rate. And then also this extra resistor here gives you extra protection because the inputs are very sensitive. They simply degrade all characteristics like the input offset voltages, the input bias current, etc., can degrade. Even if this happens only once, even for only milliseconds, your op-amp could lose its specifications. So, very simple way. And we have seen you always have to consult your datasheet about the characteristics. Where is there internal protection? Is there ESD protection? What can the output deliver? What is allowed as current, maximum current at the inputs, etc. And so with these 4 passive elements we have nearly perfect protection. If we now still add the ESD protection diodes here, we can be 99% sure that whatever comes as a signal at our input, our first op-amp, and that is the one that has to be the best protection, will never be damaged, destroyed, or lose its specs.